Hey y'all, welcome to a long overdue lecture on redox reactions. Somehow, with paternity leave and some travel, this lesson that should have been in the early part of the semester is now being delivered in the latter half. But I thought it was important that we sort of at least go over some redox reactions. A lot of these ideas are probably familiar from your chemistry classes, but we're going to put them in the context of water quality and specifically sort of biogeochemical reactions. So, just some review to start. Um, the goals for this lecture are to review redox reactions from a general perspective, so just kind of a reminder of your chemistry class, discuss why redox chemistry is important for water quality, and then review this idea of the redox ladder, which is an important control on how we manage water quality and how water quality varies in nature. I just have some videos showing sort of like interesting redox reactions. So this is a video that you can find on YouTube pretty easily, but basically it's just this idea that there's carbon impurities in iron, and if you heat iron up a bunch and you chuck these iron filings up against a wall, you create a redox reaction, and redox reactions are the exchange of electrons, and so often that creates light in this context. So it's this very like nice I think video showing that, so you should watch that later. I'll put a link in the description. And then another famous sort of redox reaction is putting alkali metals in water. So you can watch this video. They're just sort of explaining this reaction, but they put rubidium in that little tank of water and it caused an explosion. And that's just the super rapid exchange of electrons causing that. So these are sort of the probably the things you remember from chemistry, general chemistry, redox reactions. It also is the kind of reactions that powers batteries because, again, it's the exchange of electrons between different elements or compounds. I'm not going to go super deep into redox chemistry itself. I think this Crash Course Chemistry number 10 video does a great job going over the general ideas of redox reactions. So you should watch this. There'll be quiz questions relevant directly to the content inside this video. They do a great job over at Crash Course sort of explaining how this works. I'm going to sort of focus on a general review just so we can talk about how it affects water quality. So, oxidation reduction reactions are about reducing and oxidizing compounds. So in this context, A is a element that is going to be oxidized, and oxidized means losing electrons. And so once the compound has lost its electrons, it's called an oxidized compound. When it had all the electrons, it was called reduced compound. And the reaction here is exchanging these electrons across this red line. And in order to exchange those, you need one compound A that has a bunch of electrons and one compound B that is hungry for electrons. And so we have this oxidized compound B, and B gains the electrons, and then it becomes a reduced compound. So reduced compounds have extra electrons, and oxidized compounds have no extra electrons. And when you exchange these electrons, that sort of can create energy, both in the terms of like if this were a reaction in a battery, it powers your cell phone, but also in terms of life. So this energy of exchanging electrons is all of the energy that powers sort of life, is these redox reactions of electrons moving from essentially A to B. So just some reminders about redox chemistry. Redox stands for reduction oxidation reactions, which is basically who is getting and who is giving and who is getting the electrons. So electrons are always exchanged in a redox reaction from one atom to another. Atoms that gain electrons are called reduced, and atoms that lose electrons are called oxidized. And you probably remember this from high school chemistry, but oxidation is loss and reduction is gain. I still have to use that trick all the time. So by the end of this lecture, we should be able to break down a redox reaction and figure out in these compounds which ones gain and lose electrons. So this is just a lithium breakdown. That explosion video, lithium does the same thing, but not quite as violently as rubidium. So lithium, we'll figure out how to sort of break down who gets the electrons in this reaction. So to do that, we need to review this idea of oxidative state or oxidation number, which is a simplified way of keeping track of electrons. And then you can follow 8 rules to figure out the atomic oxidative state of compounds or elements. So we'll run rule 1 is if a single element is self-bonded, then the oxidation state is 0. So something like oxygen, O2, that means that the oxidation state is 0 because it's bonded to itself. If you're doing nitrogen, N2, self-bonded, so the oxidation state is 0. If you're doing hydrogen gas, H2, again, self-bonded, so the oxidation state is 0. Monotonic ions have oxidation state of their charge. This one's probably the easiest one. Sodium plus has a +1 oxidation state, and chloride, which is chloride -1, has an oxidation state of -1. So these ones are sort of the easiest to read when there's just a single monatomic ion. So if you had calcium 2+, it would be +2. This is where online delivery, I would normally ask the class to give some examples, but you know what I mean, hopefully by now. Rule 3 is that alkali metals always have +1 oxidation number. So this is lithium, sodium, potassium, rubidium, cesium, and francium. And basically that is a sort of rule. We can see sort of why lithium and sodium and potassium are all have oxidation numbers of +1 if we take a look at their sort of electron orbitals. So what you can see here is lithium has this outer electron shell. It only has 1 in that shell, and it could have a bunch more. It could have 8. And so instead of sort of trying to gain 7 more electrons, what lithium will do is frequently donate this electron. And that would be true of sodium and all the other ones because of these outer electron orbitals aren't filled. And so they donate one away, and then their electron sort of shells are filled properly. It's okay if you don't deeply understand this, but this should just be a reminder of some ideas you covered in chemistry. Similar to alkali metals, alkaline metals, second from left on the periodic table, have an oxidation of +2, and it's a similar idea. It's the electron orbital sort of filling idea. So that's beryllium, magnesium, calcium, etc. Hydrogen is +1 when bonded to a nonmetal, and hydrogen is -1 when bonded to a metal. Oxygen is almost always -2. For most of our purposes, it always will be -2, unless it's in a peroxide, which is H2O2. Then it's -1. Rule number 7, fluorine is pretty scary, and that's because it's always -1. So fluorine is always trying to scavenge and find one more electron to fill its outer orbital. So it's sort of the inverse of lithium. It really is hungry for another electron. Rule 8, this was sort of summing them all up. Basically, the sum of the oxidation numbers in a molecule is 0 or the charge of the molecule. So for sodium chloride, you have sodium, which is +1, chloride, which is -1. That sums to 0. So the oxidation number of the whole molecule is 0. Whereas the sulfate, the oxidation number is -2. And that's basically because oxygen is, if you sort of do the math here, oxygen is -2. -2 times 4 is 8. And then you have already 8 accounted for here. So we need to do 8 minus 2, and so that equals 6. So sulfur here has an oxidation number of +6. If that makes sense, that's sort of how you figure that out. So why do we care about oxidation number? Well, it's a way to think about which elements receive and give the electrons, and it's these reactions that sort of maintain life, and they depend on that electron exchange. And so we need to figure out who's gaining and losing electrons in order to understand these sort of basic water quality reactions. When we've talked about anoxic conditions in class, or adding bleach to disinfect water treatment plant to add disinfectant at water treatment plants, that all goes back to these ideas about sort of electron exchange and changing oxidation numbers. And so it's sort of the core of how we manage water quality and also how we understand water quality in the environment. So now we can sort of break down this lithium reaction. So 2 lithium, which is a solid, has an oxidation state of 0 because it's self-bonded. 2 H2O, so H2 bonded to a nonmetal, so it's -1 times 2, so that's -2, and that, of course, bonded to a nonmetal, so it's +1, so +2, and then oxygen is -2. So now we have lithium bonded to oxygen and hydrogen, so oxygen is -2, hydrogen here is +1, and that means lithium is -1, which is what we would expect, and H2 gas is 0. So basically, in this reaction, what happened is two lithiums donated their electrons to hydrogen gas. Um, so that's sort of what causes that rapid explosion. Another core idea that we're going to sort of discuss a lot in the assignment is this idea of redox potential. And redox potential can be measured with a measure called PE, or electron potential. And so that's like pH. And so we call it electron potential. And this value can essentially be interpreted as positive value means a solution will likely oxidize a new chemical species. So it'll take the electrons from that new species. Whereas negative values means that the solution will reduce new chemical species. So they will donate electrons. So positive values mean that you're full of space to take in electrons. Negative values means that you basically have so many electrons already in the compounds that you want to donate them. Positive values are well oxygenated turbulent waters. If we're thinking about streams, they will frequently have a positive oxidation reduction potential or electron potential. And values in slow moving or stagnant waters can often be negative. There's another sort of set of ideas that now we're getting really into the biology, but basically redox potential also describes the amount of energy that different life forms get based on the sort of where they're who is donating the electrons and who is sort of the final electron acceptor. And so we're often used to thinking about how humans sort of process energy, and we of course breathe oxygen, and that's down here in the sort of bottom left of this figure. That means that oxygen is our final electron acceptor, and it's usually by what is donating electrons is organic carbon, and oxygen basically has a very high efficiency. So you get a lot of energy out of this reaction, but it's not the only reaction in life where you can have a final electron acceptor. So if we move over to the right, we can also have denitrification, where you would have a nitrate molecule is the final electron acceptor, and you're still using organic carbon as the sort of electron donor. So on the bottom left here is where is the energy coming from, and on the top left is sort of where is it going. And so it's going to convert nitrate to nitrogen, and you can do that with iron, ferrous and ferric iron, and you can do that with sulfate as well. And there's a bunch of other biogeochemical reactions. But these reactions sort of describe decreasing energy yields. So you could be in a turbulent freshwater stream, and most of the reactions that you'll sort of measure are going to be these oxic ones because there's plenty of oxygen. But let's say now you go to some pond next to the stream. At the bottom of that pond, you might have a bunch of denitrification because there's no more oxygen left. And so the next most efficient thing to do is to denitrify nitrogen. And then once you're done with all the nitrate and there's none left, now you might start to reduce the iron. So you just sort of like go down this redox ladder, and that you get decreasing energy yields. And so that's really important because this sort of sets up what reactions are available. If you're at a wastewater treatment plant, you really want to make this denitrification reaction happen. So that means you have to get rid of all the oxygen. We can look at redox potential, the sort of amount of energy across a variety of elements. Only some of these are sort of biologically relevant, but you can see the oxygen up here is a very sort of efficient reaction producing a lot of energy. And that's what that reduction potential is. And then if we crawl down, we see nitrate. We see oxygen again with a slightly different reaction. And then we can just sort of keep crawling down. A lot of these are sort of like battery reactions. Okay. And then now we get to the sort of final idea that there's this idea of a redox ladder. And so that's the types of reactions that'll go on in a decrease, and they'll provide decreasing energy for the organisms doing them. So we have oxidation reduction, we have denitrification, we have manganese reduction, iron reduction, organic carbon reduction, sulfate reduction, and then CO2 reduction. This is sort of methanogenesis here. So this is sort of where methane comes from. And basically, as you go down this ladder, you're decreasing the energy efficiency. And so depending on the concentration of these different elements, you'll have different reactions available, and there's different microbes that can do different parts of these reactions to sort of basically chew on carbon and produce energy. And so that's sort of what this redox ladder highlights. And if you're a wastewater treatment plant manager, you really want to pay attention to this, because you're going to be manipulating your waters to sort of encourage denitrification, to get rid of nitrogen in your water. So those are sort of the core ideas I wanted to go over today. The assignment goes a lot more in depth into oxidation reduction potential, and dissolved oxygen dynamics in streams. So yeah, I'll see y'all tomorrow.